I will be discussing rockets today. Forces. Force of gravity. The equation listed for force of gravity is a gravitational constant times mass 1 times mass 2 divided by r squared. This equation is more useful for whenever a rocket is on another planet, such as the moon, when the mass is different and the radius from the center is also different. The second equation is much more familiar with mass times acceleration, with acceleration being equal to 9.81 meters per second squared. As you can see, there are some values that important values that are listed also, such as the gravitational constant and the mass of the Earth. How it influences design. Since the force of gravity is directly correlated to the mass of the ship, it's therefore important to reduce the mass of the ship as much as possible. This is also why such little cargo is carried on rockets, because most of the available space they use for fuel. On the diagram on the right, we can see that weight and the force of gravity are the same value. Air resistance, which is just a form of friction. The equation behind air resistance is quite complicated and depends on many factors, such as the area of the object, the velocity, and the density of the air. How it influences design. Engineers want to leave some air resistance because they don't want to reduce the weight or have extra thrust, which is why all rockets have aerodynamic designs. This means that they're very tall and they're very narrow. So on the diagram on the right, we can see that drag and air resistance are the same values and they all both work against the rocket. And on the diagram below that, we can see that all rockets follow the same design of narrow and tall, all in an effort to reduce the air resistance. Thrust, which is just applied force. The equation for this is listed on the slide, and what it basically means is how much mass is being ejected from the exhaust and at what speed they are. The applied force comes from a chemical reaction within the engine, and the products escape at high velocities, which accelerates the rocket. So how it influences design. There are a lot of design modifications which take into mind the thrust. For example, the direction of the nozzle. Rockets only move in the opposite direction of the nozzle, which is why all their nozzles are at the bottom. But there are also some engines on the side to control pitch, yaw, and roll. A lot of consideration is also put into whether the engine is operating in a vacuum or Earth's atmosphere. So on the diagram on the right, we can see that thrust is pushing the rocket up. And on the diagram below that, we can see SpaceX's Starship rocket, which actually uses gimbals to steer their rocket. Physics principles. Some physics principles found in rocketry include Newton's first law, which states if an object is at rest, it remains at rest, and if it is in motion, it remains in motion at a constant velocity unless acted upon by a net external force. This is very relevant in rocketry. If a rocket is traveling with a net external force of 0, especially when it is in space, we will know that it will travel at a constant velocity. Another physics principle is Newton's second law, which states that the force is equal to mass times acceleration. This is very important because we want to know how much force is being applied to the rocket and how much we need to actually get into orbit, during liftoff, and when it's re-entering. Another of Newton's third law is found here, and it is Newton's third law. For every action, there's an equal and opposite reaction. This is very fundamental to how rockets work, which propel propellant out from its exhaust, which pushes the rocket forward, because there is an equal and opposite force. And another physics principle is relative velocity. Earth is traveling at about 1600 kilometers per hour at the equator, which is very important to know, especially when launching rockets, because this is the speed needs to be added on top of whatever the rocket gains from thrust. Development timeline. The first rocket to reach space was the German V-2 rocket, which was created during World War II as a weapon. Afterwards, American and Soviet scientists built off that research to develop their own rockets. These first rockets were mainly used as ICBMs with nuclear warheads. However, rockets for space exploration shortly took off with the first human Yuri Gagarin in space. Developing rockets can take a very long time. For example, the Saturn V went through 8 design changes. Manufacturing a rocket can be even more difficult because of the complexity of the rocket. For example, the Falcon 9 takes approximately 18 months to be constructed, whereas a rocket that is designed to carry humans, like the Space Shuttle, can take up to 5 years to be constructed. On our right, we have a German V2 rocket, and below that we have the SLS rocket, which is designed to take humans back to the moon, and this specific rocket has been in development for 10 years. Advantages and disadvantages. The number one limiting factor of rockets is the price tags. Rockets are very expensive to develop and manufacture in lots. So here's some statistics. For the Saturn V rocket, it took $34.4 billion just to research, develop, and fly it. Now for SpaceX's Falcon 9, it is much more current, but it still costs a whopping $62 million per launch. Another drawback is that there's very little demand of sending anything into space. Frankly, the vast majority of people don't need things sent into space. It's mostly governments and communication companies that need things sent in space. For just a figure, there were only 95 launches in 2019. Another drawback is that there are a lot of people who question if it is wise to spend so much on rockets. For example, during the space race, the United States and the Soviet Union spent huge amounts of money in the space race. This money could have gone to improve people's lives instead. Now, if you go on the right, we can see a screenshot of SpaceX's website showing the price per launch, and at the bottom, it is a artwork suggesting that there may be another space race in the future. There are some advantages to rockets. The first main advantage is that technology could be used for national security. Rockets were originally born out of the need to transport explosives over long distances, and ICBMs are basically just rockets. And so any technological advance in rockets benefits the military as well. Rockets can also support other industries. I talked about how communication satellites need to send their own things up there too. And because of this, we have GPS, television, and internet in some remote places. Rockets also allow the International Space Station to exist, which allows it to conduct experiments in space which will benefit humans later on. Another advantage, which is very useful in the long term, is that it will allow humans to become multiplanetary. It is very important for humans to become multiplanetary because it is a matter of not if, but when next mass extinction will arrive. This extinction can also cause the extinction of our species, and it's important that we try to colonize as many planets as possible to preserve our species. Improvements made to design. Main efforts behind improving the design of rockets are made to reduce the cost. For example, SpaceX has reusable rockets which can land on their own. This can drive down costs by a huge margin. Other ways to reduce costs include more efficient engines and more efficient manufacturing processes. Another key aspect of design to rockets is their safety. Rockets are still pretty unreliable. For example, SpaceX's Falcon 9 has a success rate of only 94%. This is good compared to other competitors, but having an expensive rocket fail 6% of the time is still unfavorable. We also want to avoid accidents like NASA's Challenger and Columbus explosions, which caused human deaths. Another key aspect of improvement is being able to return to the moon and then further on to Mars. Recently, NASA awarded contracts to SpaceX, Dynetics, and national team to develop a lander to get people back on Mars, and this requires rocket technology, and this will come with innovation as well. And on the top right, all the dead red boxes represent the number of times it failed, and we can see that there are quite a large number of failures, which is why we need to improve safety, which will later on reduce costs as well. Social impacts. Some social impacts of rocketry is that there are many people that are interested in the field of rocket astronomy and space exploration. For example, during the space race, there's a huge amount of awareness behind space, which allowed for the support of each other for each country's space program. Another social impact is that we're just natural explorers, and that we just have a natural curiosity to explore the universe, which is why we need to develop these sorts of technologies. Economic impacts. Rockets provide many jobs, many high-skilled jobs especially. And while it's hard to find an exact number, we can infer that rockets provide many jobs in the field and outside the field, including in communications and in the military. Another economic impact, which is not so good, is the government spending. Government spend huge amounts of money behind the space program, which takes away spending money in other investments, such as schools or in like the oil fields. Another other important aspect is to consider private companies. Many private companies are taking the burden from other governments in building rockets, which does reduce the cost to the government itself. For example, we have Rocket Lab, SpaceX, Blue Origin, and ULA, which are all private companies. And yes, some of these companies do get funding from the government, but a large chunk of this money is privately funded. On the right, we can see a chart showcasing the U.S. government spending on NASA as a percentage of its national economy, and we can see that it does take up a huge chunk of, or not necessarily a huge chunk, but a sizable chunk in the U.S. economy. And below that, we can see a few aerospace companies around the world. Environmental impacts. Many people are worried about the exhaust that comes from rockets. However, this is rather pointless, as the exhaust of rockets is pretty harmless, considering that it is mostly CO2 or water vapor. For example, if you look at the Falcon 9, it mostly just emits CO2. Well, there is a space shuttle in the SLS which do emit more fumes, but they have launched so little that it really does not make an impact. Now, for manufacturing rockets do have a negative impact because it requires huge amounts of resources, including minerals, water, and energy. Transporting rockets to the launch site can also have environmental consequences. Another important issue to raise is space junk. There are a lot of debris flying around in Earth's orbit that can be dangerous to other satellites and to other people. But however, the vast majority of rockets that are sent to space, they usually burn up in the atmosphere a few days later, so there's not too much to worry. Overall, I believe that rockets have a negligible impact on the environment because they are flown so few times compared to cars and airplanes, which are used daily in huge amounts. On the right, there's a graph showing all the exhaust fumes from each rocket, and in the photo below, this is just an exaggerated photo of all the space debris in Earth's orbit. All this debris is sized up to make it visible, but in real life, it looks nothing like this. Careers. Rocketry requires many people to work together. These people include engineers from chemical, aerospace, material, or electrical engineers. They also require a lot of high-skilled construction workers to build rockets with extreme precision and accuracy. We also need ground support workers who help the rocket launch. These people can be people who actually cover the launch on TV, or they can be people working in mission control. On our right, we can see that we have a screenshot of SpaceX's hiring screen, and we can see there are a multitude of jobs available within this field. This is the end of my video, and I hope you enjoyed it.